In this module, we will introduce the topic of catalysis. Catalysis plays a decisive role in the chemical industry, supporting the production of a vast majority of chemical products. For instance, the transformation of crude oil into fuel is facilitated by catalysts. Similarly, the synthesis of most chemicals and materials relies heavily on catalytic processes. Moreover, catalysis is increasingly employed to reduce or prevent waste and pollution. This highlights the significance of catalytic processes not only for efficient chemical manufacturing but also for the environment. But what is catalysis and catalyst? Historically, the term catalyst was defined by Wilhelm Ostwald, a pioneer in the field who received the Nobel Prize in 1909 for his contribution. Ostwald described a catalyst as a substance that increases the rate of a chemical reaction without being consumed in the process. Importantly, a catalyst accelerates the reaction process but does not modify the final thermodynamic equilibrium of the reaction. This unique characteristic of catalysts to speed up reactions without undergoing any net chemical changes is what makes them invaluable in various chemical processes, including those in industrial applications. A catalyst primarily influences the pathway of a chemical reaction. By offering an alternative route, it effectively lowers the energy barrier, the activation energy, required for the reaction. This is achieved through the introduction of a new reaction mechanism involving the catalyst, creating a secondary reaction coordinate that connects the reactant and products. The key here is that the activation energy along this new pathway is lower compared to that of the uncatalyzed reaction. Consequently, this results in an increased overall reaction rate. Catalytic processes are typically represented using energy diagrams, as illustrated in this figure. In such diagrams, the vertical axis represents the potential energy, while the horizontal axis denotes the reaction coordinate. The diagram compares the activation barriers of uncatalyzed and catalyzed processes. For an uncatalyzed process, the activation barrier is higher, depicted by a taller peak on the energy diagram. In contrast, the presence of a catalyst provides an alternative pathway with a significantly lower activation barrier, represented by a smaller peak. This lower activation energy for the catalytic process results in an increase in the rates of both the forward and reverse reactions, thereby accelerating the overall reaction process. This visualization effectively demonstrates how catalysts function by offering an easier road for the reaction, which requires less energy to overcome. A crucial aspect of catalysis, which is also taken into account here, is that the catalyst does not influence the initial and final states of the reaction. This means that the energy released during the process, which is the difference in potential energy between the initial and final states, remains unchanged by the presence of the catalyst. The catalyst's role is confined to altering the reaction pathway, but it does not affect the overall energy change of the reaction. The energy released or required for the reaction, the difference in potential energy from start to finish, is the same with or without the catalyst. This principle underscores the fact that while catalysts can significantly speed up reactions, they do not alter the inherent thermodynamic properties of the reaction itself. In typical two-dimensional representations of catalytic processes, such as energy diagram, an important aspect is often not fully conveyed. The entire reaction pathway is altered by the catalyst. While these diagrams effectively show the reduction in activation energy due to the catalyst, they may not clearly illustrate that the catalyzed reaction follows an entirely different path. The catalyzed transition state not only has a lower activation energy, but also represents a fundamentally different reaction mechanism. This distinction is crucial for understanding the role of catalysts. They don't just lower the energy barrier, they change the road of the reaction, offering an alternative pathway that is more energetically favorable. However, this change in the reaction pathway is not always apparent in simple two-dimensional energy diagram. It is essential to understand that catalysts do not magically initiate entirely new reactions that are thermodynamically unfavorable. Their role is to enhance the speed and efficiency of reactions that are already spontaneous from the thermodynamic point of view. Catalysts work within the boundaries of thermodynamics. They do not alter the final outcome of the reaction. Instead, they assist in the process by creating a new, more rapid and more efficient reaction pathway. By doing this, catalysts make reactions more practical and accessible in various chemical and industrial applications. Another aspect of catalysis is the decrease in energy consumption. While non-catalytic processes can be imagined as being complicated and demanding, catalytic processes discover a more efficient pathway for the reaction. This efficiency not only speeds up the reaction but also allows to perform them in an energetically more favorable way. A fundamental aspect of catalysis is that the catalyst remains unaltered and is not consumed during the reaction process. Catalytic processes can be typically represented as a cycle where the catalyst effectively regenerates itself during each reaction cycle. During the catalytic cycle, the catalyst interacts in some way with one or more reactants or intermediate species involved in the reaction. These substances may form catalytic complexes or transition states or become bound to the catalyst by some means. The reaction then proceeds with the participation of the catalyst. It leads to the formation of the product, which is subsequently released. The catalyst is not consumed but returns to its original state and becomes available to interact with another reactant or intermediate in a subsequent reaction cycle. This cyclic nature of catalysis ensures that even a small amount of catalyst can facilitate numerous reactions. Catalysis is a multidisciplinary and interdisciplinary field spanning a wide range of scientific domains from biochemistry to surface physics. This diversity reflects the universal nature of catalytic processes, which are fundamental in various scientific and industrial applications. In biochemistry, enzymes act as biological catalysts, facilitating complex biochemical reactions essential for life. On the other hand, in surface science, catalysis is essential for understanding and manipulating reactions on material surfaces, which is vital for numerous industrial and technological applications. The broad spectrum of catalysis applications highlights its significance and versatility in both natural and engineered systems. In the study of catalysis, we typically distinguish between various types of catalytic processes. These include homogeneous catalysis, heterogeneous catalysis, and biocatalysis. Each of these categories represents a separate approach to catalysis with its unique characteristics, specific advantages, and applications in various fields. Homogeneous catalysis is characterized by the catalyst and reactants being in the same phase, typically in a liquid form. It includes, for example, acid-base catalysis or catalysis by transition metal compounds. In homogeneous catalysis, the uniform distribution of the catalyst throughout the reaction medium allows for efficient interaction with the reactants. This can lead to more effective and controlled reactions, as the catalyst can uniformly influence the reaction process. Homogeneous catalysts are particularly useful in facilitating complex organic synthesis processes. They are widely used in various chemical industries for the synthesis of pharmaceuticals, polymers, and fine chemicals. Heterogeneous catalysis occurs when the catalyst and reactants are in different phases. An example of heterogeneous catalysis would be a solid catalyst accelerating a reaction between gaseous or liquid reactants. In heterogeneous catalysis, the reactants adsorb into the surface of the solid catalyst. The reaction occurs on the surface of this solid catalyst. This process can involve inorganic catalysts and biocatalysts. The latter we will consider separately. In the realm of inorganic heterogeneous catalysts, there is a further distinction between full catalysts and supported catalysts. Full catalysts refer to catalysts where the entire bulk of the material is catalytically active. Supported catalysts consist of an active phase dispersed on a support. Support is the material that is primarily employed to increase the surface area of the active phase and maintain the small size of the active particles. A classic example is the automotive exhaust catalyst, where fine platinum nanoparticles are distributed on an oxide support. The dispersion on support not only helps to keep the particles small, but also facilitates mass transport, processes essential for the catalytic action. The interaction between the solid catalyst surface and the reactants leads to a variety of reactions pathways, making heterogeneous catalysis a complex field of study. Heterogeneous solid catalysts are common in large-scale industrial processes where they are used to facilitate reactions of gases or liquids. They are employed due to the ease of separation from the reaction mixture and their ability to be used in continuous processes. These catalysts often exhibit high stability and can be used over extended periods, making them economically advantageous for industrial applications. Biocatalysis refers to the use of natural catalysts, such as enzymes, to facilitate biochemical reactions. Enzymes are highly specific catalysts, accelerating only certain reactions with particular substrates. This is a key feature distinguishing them from other types of catalysts. Enzymes as catalysts are a special class within the realm of catalysis. They can be characterized as solid-phase catalysts, while the reactants are typically in a liquid phase. Depending on reaction environment and aspects considered, biocatalysis is sometimes classified as homogeneous catalysis and other times as heterogeneous catalysis. Very generally, a catalyst's performance is typically characterized by two key attributes: its activity and stability. When comparing catalysts, the term activity is often used to describe their efficiency. The activity of a catalyst is typically understood as its ability to accelerate a reaction compared to the reaction rate in its absence. However, the definition of activity can vary across different fields and types of catalysts. Furthermore, due to the diverse nature of catalytic processes, the comparability of activity across different catalyst types can be complicated. In addition to activity, the lifespan or stability of catalysts is crucial for their practical application. Despite the theoretical definition of a catalyst as a substance that remains unchanged by the reaction it catalyzes, in reality, the lifespan of catalysts is always finite. This limitation is significant, for example, for their deployment in industrial processes and must be considered when evaluating catalyst performance. The point at which a catalyst becomes inactive is vital for cost considerations in any industrial process. Understanding and predicting this point is essential for efficient and economical operation.